김태현 교수님께 감사드립니다. So I think I need to switch to English. So my talk is in 4 sections. I first want to talk about some simple idea which is called singular weights. And then I want to talk about what is minimal model program, which is in the title. This is a branch of algebraic geometry. And then we need this notion of plurisubharmonic function and the multiply ideal sheaf of such a plurisubharmonic function. And then the last section is on a question about this notion of multiply ideal sheaves. Okay, so let me start with this really simple looking question. So let's consider several complex variables. So z1 through zn are complex variables, and f is a holomorphic function on those variables. And we want to consider, given this holomorphic function, we want to consider this real value function, which is the absolute value of f to the power of 2 times s, 1 over absolute value of f 2 times s. And we ask for which real numbers s is this function locally interval. So when s is negative, of course, it will be continuous and it will be locally interval. So for those positive real numbers s, this question makes sense. So here local interval means when you integrate this real value function on small open subsets, you want it to be you want this integral to be finite. So when the integral is finite, we say it's integrable, and when the integral is infinite, we say it's not integrable. 제 목소리 잘 들리시나요? 네. Okay, so depending on what this f is, this question could be easy or quite difficult. So let's consider the following, the simplest example. When you have one variable and the function is simply z, then the question is whether this integral is finite for some values of s. And actually it turns out that this is finite exactly when s is less than 1. When you take this w to be a neighborhood of the 0 point. So when f is 0, we want to say the function has pole at those 0 points. So for this calculus type question, you can use polar coordinates. And when s is 1, so when s is 1, the integral is infinite. And you can also easily show that when s is less than 1, the integral is finite. So there is this one value of s where finite becomes infinite. So there's sort of a critical value for this finiteness of this integral. When s is less than 1, it's finite, but when s is 1 or above, then it becomes infinite. And the picture is same when this function defines a non-singular hypersurface. So when you have not just one variable, but several variables, and when f is giving a non-singular hypersurface, then you have the same critical value, which is 1. Then the picture is different for the case when f has some singular point. So one simple case when f has singular point is like this, when f is of 2 variables and the function is z squared minus w cubed. So in this case, there's only one singular point of the 0 set of this f, which is the origin. So the partial derivatives of f with respect to z and w, they are 0 precisely at this one point, which is the origin. And it turns out that this is finite if and only if this number s is less than 5/6. So that 5/6 appears when you consider the resolution of singularities of this singular curve, or the singular zero set. So you blow up the origin a few times, and then basically you can use the previous situation where you had this non-singular hypersurface. So basically you use this geometry to have this critical value of 5/6. Sorry. Okay, so we can imagine that when f is a much more complicated holomorphic function, then it will be more tricky to find the value which you can put here. Actually, it will be always a rational number, but it's not easy to compute. So now we want to give a name for this kind of real value function. So we want to call it a singular weight. So it's singular in the sense that when f is 0, this function is infinite at those points. And in particular, for some given value of s, when this is not locally interval, we want to say it has non-interval singularity. And here's a piece of notation which is exponential minus phi. We often want to write this singular weight as exponential minus phi, where phi is 2s log of absolute value of this holomorphic function f. Okay, so when the singular weight exponential minus phi is not integrable, we want to consider some functions g such that when you multiply the weight by this g squared, it becomes finite. The integral becomes finite. So without multiplying this g, it will be infinite when it's non-interval. And you can collect all those functions g, which makes this new integral finite. So basically, what you need for g is that it should have some zeros along the 0 points of f, so that it can cancel out the poles coming from the 0 of f. So, so how much 0 g needs to have at those points, it's not clear, but there must be some amount of zeros you can require g to have, so that this is finite. And when you collect all those g's, it forms an ideal in the ring of holomorphic functions. And we name this ideal as the multiplier ideal of this singular weight exponential minus phi. So for different holomorphic functions f, you will have different ideals in the ring of holomorphic functions. So we want to talk about the relation of this notion to algebraic geometry. Up to this point, everything was calculus in terms of complex variables. So let's recall some basic notions in algebraic geometry. We have this correspondence between ideals in rings and submanifolds or subschemes. So when you allow some singular points in some manifolds, then it is subvarieties. And when you allow some nilpotent functions, it becomes subschemes. And in complex analytic geometry, the subscheme is the same thing as subspace or subanalytic space. So as a very simple example, when you consider this ring of polynomials in two variables, if you consider the ideals generated by z and also the ideal generated by z squared, both of them give the same set of points, which is the line in the complex two-dimensional plane. but they are giving two different subscheme structures on the line. So using the ideals, we are distinguishing those different subschemes. And so we had just defined this multiply ideal, and what it does is that it is measuring the amount of non-interval singularity of the singular weight. So when the weight is interval, then you will have empty set in the place of z. Okay, so it's basically measuring the amount of non-interval singularity. So for example, in the earlier example when we had this z squared minus w cube, for this 5/6, the multiply ideal becomes non-trivial. When s is less than this number, the multiply ideal is trivial, but now it's non-trivial, and it is equal to the ideal of a point, the origin in C2. So every function that belongs to this ideal has this local interval property, which means that the g absolute value squared times exponential minus phi will be locally interval. Okay, so we have some more basic notions in algebraic geometry. So we already said what variety is, but one more time, a non-singular complex projective variety is simply a closed submanifold of the projective space. And when you don't use non-singular, in general, a variety may allow some singular points. So the simplest example of non-singular projective variety is when the dimension is 1, and in that case they are called compact Riemann surfaces. So there are lots of things you can say about Riemann surfaces, but one thing, one very rough classification is that in terms of genus of X, you can put all compact Riemann surfaces into three classes. So when genus is 0 and when genus is 1, it corresponds to elliptic curves, and all the others form the third category. And instead of, in terms of genus, you can also use the canonical line bundle Kx. So we'll talk about it in the next slide. So we have this notion of positive and negative for line bundles. So the first case corresponds to when Kx is negative, and the last case corresponds to when Kx is positive. Okay, so we just talked about this canonical line bundle, and more generally, a general line bundle L is something determined by the data of transition functions. So of course, line bundle is the special case of vector bundle whose rank is 1, but a very convenient view, a convenient way to think of line bundle is it's given by these transition functions Gij when you fix an open covering of Uj. And then holomorphic section plays an important role in this talk. And holomorphic section is something like a holomorphic function, but you have a family of those functions satisfying this relation in terms of transition functions. And we find the mth tensor power of a line bundle to be another line bundle, which is determined by the new transition functions, which is Gij to power m. And when X is non-singular, we can define a especially important line bundle, which is Kx, and this is defined as the nth wedge power of omega x, where omega x is the cotangent bundle of a complex manifold X. So this is called canonical line bundle. So we can think of holomorphic sections of this particular line bundle Kx to be locally some holomorphic functions times this differential form dz1 through dzn. Okay, and then when you have some holomorphic sections of a line bundle, what you can do is you can define a map from that variety to another variety. So suppose that X is a general variety and L is a line bundle, and you have these a finite number of sections, and then this map is defined by this rule, sending a point to this homogeneous coordinate, and this homogeneous coordinate is well defined as long as all these sections don't have a common 0 point at P. So in such a case, we say the line bundle is base point free. So in other words, if you have enough number of sections which does not have any common 0 point, then we say the line bundle is base point free. Otherwise, the sections may have some common 0 points, and they are called base points. And we also think of this vector space of all holomorphic sections, and it can be also named as a linear system. So when you have some base points, this rule still works in the sense that except those points where it's not defined, it is still giving some kind of map, which is called a rational map, in the sense that it may not be defined as some subset of points. Okay, so we don't have enough time to talk about more algebraic geometry in this talk, but I want to at least say what this MMP is, which is in the title. So this is a series of results and conjectures, and the main conjecture is as follows. Let X be a non-singular variety of general dimension, and suppose that there exists at least one integer m such that kx power m has at least one non-zero global holomorphic section. So actually, the holomorphic category is different from the differentiable category. Often it's not trivial to construct holomorphic functions or holomorphic sections under conditions. So under this assumption, we have the following conjecture, which is that there is another variety y, and this y cannot be guaranteed to be non-singular. It could be having some singularity, and we want this y to be birational to x, which means that there is a rational map from y to x and another rational map from x to y, and they are inverses of each other, so they are birational. And for some other integer m, which is maybe different from this m, the new variety, the canonical line bundle ky of this new variety has a very nice property. Its mth tensor power does not have any common 0 points. So as defined previously, this mth power of ky is base point free. So it's defining a map from y to another variety. So when ky has this property, it's considered to be a very nice property of this ky. In general, we cannot expect the same property for x. So that is why we need this birational model y of the original variety x. So for example, when the dimension is 1, this is not a conjecture, because in dimension 1, if two smooth varieties are birational to each other, then they are actually isomorphic. So anyway, this is mainly a conjecture for dimensions at least 2 and above. So one remark is that, as I said, we cannot expect y to be always non-singular. So people had examples where you need y to be singular from the 1970s. But the allowable kind of singularity in this conjecture is actually very mild, and it was extensively studied and now well understood. So I cannot go into details of this theory of singularity, but essentially I could say one needs is that the volume form of X to be locally integrable. So this property is trivial for smooth non-singular x. But for some singular varieties, this property can still hold. So we only consider those singular varieties to formulate this conjecture. So we don't go into details about this area of algebraic geometry, but let me briefly say that when the dimension is at most 3, it had been proved by work of many people, and particularly Mori, Kawamata, Miyaoka. And there have been lots of activities in this area from the late 70s. So of course I cannot name all the people, but I need to mention that recently, about 5 years ago, there was this work of Birkar, Cassini, Haken, and McKernan, and they had a breakthrough result toward this conjecture for general dimension n, but it is actually far from the full solution of this conjecture. Basically, what they have is they can prove that there is such a y when kx satisfies some condition which is called bigness condition, and they can prove that ky has property called nef, which is not exactly the same as base point free, actually much weaker than base point free. So instead of talking about many results and theorems in this area, I want to point out some observation about useful methods in this area. So this will be very sketchy, but I want to make relation to the notion of multiply ideals, which appeared in the first part of the talk. So I want to name it as unreasonable effectiveness of non-interval singularity in this area of MMP. So it was first used by Kawamata and Shokurov in 1980s. So it is as follows. Suppose that you want to show the existence of a non-zero global holomorphic section of this line bundle Kx tensor L. So such a line bundle is called an adjoint line bundle. You don't just have L, but it's tensored by Kx. And actually, many geometric problems reduce to showing the existence of some sections. So actually, simply speaking, you can say that the key problem is always constructing some holomorphic sections in a given situation. So what you want to do is construct some singular weight for L. So this is like the singular weight 1 over f absolute value 2s, which appeared before. But this was actually a local function. So instead, you need a metric, which is a collection of these kind of local functions. So once you have this singular weight, and you want this singular weight to have non-trivial multiply ideal, and for convenience, suppose that this multiply ideal actually corresponds to not an arbitrary subscheme, but a nice subvariety Z. You can assume Z is smooth. So in this case, what happens is that you can reduce the problem. The problem was constructing holomorphic section. You can reduce it to the lower dimensional case. So you can expect Z to have some sections of the line bundle K times L, and often you can extend these sections from Z to back to X so that you obtain those sections you wanted to construct. Okay, so this is very sketchy, but this is one way to explain why multiply ideals are useful in algebraic geometry. And you could say this is analogous to something like differential forms with singularities. So okay, so now I'm going to another direction where we generalize this notion of singular weights. So it used to be exponential minus phi, which was equal to 1 over f absolute value to some power 2s. And it's natural to slightly enlarge the class of phi. So not just those coming from holomorphic functions, but you can take the limit of these phi's. So what kind of notion is those limit functions? We have the following standard definition from several complex variables. So instead of these kinds of phi, now we think of a new kind of phi, which is a real number and minus infinity valued function, which is not necessarily continuous, but you need it upper semi-continuous. And let's say it's defined on an open subset omega. And it is plurisubharmonic if for every complex line L in Cn, and when you restrict phi to this line intersection with omega, you want it to be subharmonic. That is subharmonic means the following inequality. For every point A in the open set omega, you want this inequality. Phi of A is less than this average over the circle whenever these points are completely contained in omega. So such property is called subharmonic, which is a notion of one complex variable. And when you require it to every complex line, it becomes a notion of several complex variables, and it's called plurisubharmonic. So it's basic fact that this phi log f absolute value square is plurisubharmonic, and we want to say PSH instead of plurisubharmonic. And you can regard this particular kind of PSH function as a special one. It's actually a very nice one, and it's called algebraic PSH. Excuse me?
In the inequality?
Yes.
So what does it have to be L?
Okay, maybe there's some typo. Sorry, you want this to be not just omega, but omega intersection with L. Yes. So, yes. Okay. So this terminology, algebraic PSH, is not standard terminology, but I think it's convenient. So we want to name it as algebraic because when phi is of this form, basically it can be understood from the viewpoint of algebraic geometry. So there are, this should be considered as a very special one among all PSH functions. And a particular example which is not algebraic PSH is this kind of function, which is minus root minus log c squared. And not just because this looks like this, there's a reason why this is not algebraic PSH. And so using this notion of general PSH function, we want to now define what's called singular Hermitian metric. So this is simply a collection of wave functions exponential minus phi k. So in this place of phi k, you can put any PSH function as far as this relation is satisfied. So you had similar transition function relation for the definition of a holomorphic section. So in that case, you had this GKL without this absolute value. But now, having this absolute value, you have the definition of a singular Hermitian metric of L. And when you have a section of L to tensor power m, actually such a section directly gives example of a singular Hermitian metric of L. Because when you have a section, you can take the local functions defining the section, And when you put those local functions in the place of f here, and then the log of absolute value becomes PSH, so you can put those PSH functions in the place of phi k. So you might think of the general singular Hermitian metric, which may not come from such sections. You can think of it as a virtual holomorphic section. It's not a genuine section, but it's something that is very close to a section. So I think one of the importance for general non-algebraic PSH function comes from the following. From the viewpoint of algebraic geometry, actually, PSH function is an important object in its own right in several complex variables. But from the viewpoint of algebraic geometry, I think we can consider the following reason for the importance. So let's define a line bundle to be effective if it has at least some holomorphic non-zero section, not just L, but when you allow all powers of L. So if at least some power m has some section, then we want to say the line bundle is effective. On the other hand, a line bundle is pseudo-effective if it has a singular Hermitian metric instead of a section. So when it has a singular Hermitian metric, as we defined in the previous slide, it may be coming from a section, but also it may not be coming from a section. And the very nice thing is that we had talked about this MMP conjecture before, and it's essentially reducing to the following very simple looking conjecture. For a general smooth projective variety X, if Kx, the canonical line bundle, is pseudo-effective, then it's actually effective. So if you only know that Kx allows some singular Hermitian metric, you can start from the metric and then eventually you can construct some holomorphic sections of some powers of Kx. So between the MMP conjecture and this simple looking conjecture, there are some steps of reduction, but those steps of reduction are not considered to be very difficult. What's difficult is this simple statement. This is very hard to prove when the dimension is at least 4 and above. When the dimension is up to 3, it was work of Kawamata and Miyaoka. So in this talk, probably this is the last point where I had direct relation to the MMP. And from now on, I want to consider a different question about the multiplier ideal sheaf of a general singular weight exponential minus phi. But this again shows the difference between general PSH functions and algebraic PSH functions. So first, we just want to generalize the notion of multiplier ideal to this general case of PSH function. So you collect all these holomorphic functions having this quantity locally interval in an open subset of Cn, and that defines the same name but more general notion now, multiplier ideal sheaf, defined by these local function germs having this quantity locally interval. So before, when you have one ring, you have the ideal in the ring, and now it's a global situation. So you have, when you have many open charts, you may have many different rings, and sheaf means that basically you have ideals in those rings in different open charts. So here is a statement which shows the subtlety of general PSH function. So let beta and phi be two PSH functions on the same open set U in Cn. And this PSH function has some simple convexity property. So when you add them together and multiply by a positive number, then it's still PSH. So you can take the multiplied derivative of this new PSH function, which is phi plus t times beta. So when t is large, it may have more singularity. So this ideal shift could be smaller. And in the other direction, when t goes to 0, you can expect phi plus t beta has less singularity. So more functions will satisfy the defining property of this multiplied derivative. So the multiplied derivative will become bigger when t goes to 0. And from the Noetherian property of the rings, we have one ideal shift j hat, which should be equal to all these multiplied ideal of phi plus t beta for small numbers of t, for small values of t. So that one ideal j hat will be contained in the multiplied derivative of phi. So let me just mention that this j hat is not the usual multiplied derivative. It's just coming from this limit process when t goes to 0. So there's this conjecture, which is called openness conjecture. It says actually these two are the same, which is the same thing as saying when you know that a function g belongs to this ideal, then you know that this interval is finite, and that equal to j hat means that actually g is satisfying a slightly stronger finiteness property with respect to not just exponential minus phi, but phi plus epsilon beta for small values of epsilon. So when beta, so for example, when beta itself is smooth, then of course this is true. But in general, PSH functions are not differentiable or continuous. And also when PSH function phi is algebraic, then this conjecture is true for a simple reason. You can again use resolution of singularities. So the problem is really in the case when phi is allowed to be general PSH, not just algebraic PSH. So this conjecture is proved in dimension 2. There's a algebraic valuation, theory of valuations due to Favre and Johnson. But for dimension 3 and above, this is a very difficult statement. So I think this statement is showing the difficulty with general PSH functions, the difficulty in understanding general PSH function. Okay, so maybe we will mention this openness conjecture later, but now we want to define another notion which is called integrally closed ideal. So in general, when you have a ring of holomorphic functions, sorry, this is typo, this should be functions, and you consider some ideal A, and we say A is integrally closed if the following is true. An element of the ring F satisfying this equation with coefficients coming from the powers of the ideal A, and Bi should be in the ith power of A. So all those F actually belongs to the ideal itself. So when this is true, then we say the ideal is integrally closed in the ring of R. And this algebraic notion of integrally closed is actually also characterized by this analytic conditions. So before, when you define multiply ideals, you are thinking about this quantity locally interval. And instead of interval, if you look at the soup form, or whether this is bounded above locally, I mean, given a singular weight and you collect all those function germs satisfying this quantity locally bounded above, then you have an integrally closed ideal, not a multiply ideal. So what's the relation between these two notions, integrally closed ideal and multiply ideal? The relation is that a multiply ideal is always integrally closed. And then you can ask whether the reverse implication holds, whether every integrally closed ideal is actually a multiply ideal. You could ask the other direction. So the first person who thought about this kind of question was Lazarsfeld. And so he had the following motivations. The multiplier ideals or multiplier ideal sheaves, they have many nice properties. So before we talked about why it is useful in algebraic geometry, but another way to talk about its usefulness is that it comes with this kind of vanishing theorem. So when you have canonical line bundle and the line bundle L tensor this multiply ideal sheaf of J of phi, so when you have suitable conditions, then the sheaf cohomology is 0 for Q at least 1. And the suitable condition is that so here I'm just saying, I'm just writing exponential minus phi, which looks like a local function, but actually this is meant to be a singular Hermitian metric. And just like the case of smooth metric, when you have a metric for a line bundle, you can define its curvature. And there's a sense of saying this curvature is strictly positive. So when this is strictly positive, then you have this Nadel vanishing theorem, which is this. So this is generalization of Kodaira's vanishing theorem in algebraic geometry. Kodaira's vanishing theorem says the same thing with smooth metric exponential minus phi. So when this is a smooth metric, then this curvature, when this is smooth metric and when the curvature is positive in the classical sense, then you have the same kind of vanishing of cohomology where this ideal sheaf becomes trivial. So you can just erase it, and you have vanishing of canonical line bundle tensor L 0. I mean HQ is 0. Okay, then most probably it may not be the case that for arbitrary ideal sheaves in this place, you don't expect to have these kind of vanishing theorems. So you want to ask how special these multiple ideal sheaves are among all ideal sheaves or among all ideals. Actually, the question is essentially local question. So you want to say, you want to ask how special these are. So Lazarsfeld formulated the question like this. We already said multiply ideal is always integrally closed. So the other direction is that is whether every integrally closed ideal equal to some multiply ideal when you choose this weight in an appropriate way. So this is again true if the dimension is 2. So there was work of these people, Favre and Johnson, and there was another work of Lindman and Watanabe, who proved that when dimension is 2, this is true. So in general, when dimension is 2 and below and 3 and above, there's a big difference. So when dimension is 2, many things in algebraic geometry are very well understood, and you can use point blow-ups to show many things, but so this should be considered as a very special case. For general dimension, actually the answer to this question is no. So what Lazarsfeld and his former student Lee, what they proved was for general dimension there is a particular integrally closed ideal, J, which is not able to be written as a multiply ideal J of psi. So given this particular J, we cannot find psi such that J of psi is equal to this J. So this was the work of Lazarsfeld and Lee. And the further question is, in this paper they are using the tools of algebraic geometry, and it's only applicable to the case of psi being algebraic PSH. So it's natural to ask what happens when you allow general PSH functions. So given this counterexample J, and when you were looking for psi within the range of algebraic PSH functions, you could not find, and whether the same is true for general PSH when you enlarge the class of functions. So we should remember this openness conjecture. The behavior of the multiply idealship of general PSH is quite subtle and mysterious. It's very different from the case of algebraic PSH function. So our result in this talk is we answer this question positively. So basically we can use the arguments of Lazarsfeld and Lee once we prove the following statement, which is called exactness of Skoda complexes. So we will talk about what Skoda complex is. It's basically a Kosul type complex involving multiply idealships. So our theorem is this. In the next slide we will define what Skoda complex is, and the observation of Lazarsfeld and actually Ein and Lazarsfeld, they first defined this Skoda complex, and they proved that it is exact. And we prove the exactness for Qth Skoda complex, where Q is at least this number. Okay, what Q and P is will appear in the next slide. And actually, this exactness is a consequence of the openness conjecture. So this openness conjecture was a statement in terms of multiply idealships. So if you assume this nice statement, then you can quite easily prove this exactness. But of course, the point of our work is that we don't use this openness conjecture. So what is a Skoda complex? Let X be a complex manifold, and suppose we have two line bundles L and M, and consider some holomorphic sections G1 through Gp for the line bundle L. And Q and P are two integers. Q is greater than P. And there is this Kosul complex which is between these vector bundles, and the maps are defined in terms of the sections. There's a particular rule giving these maps in this complex. And the definition due to Ein and Lazarsfeld is that when this line bundle M has a singular metric exponential minus psi, then in the previous Kosul complex you can insert these multiply idealships in each term, and it's still complex. So that is named as Qth Skoda complex, and which is defined by this G1 through Gp. And so it had been already known that when psi is algebraic, then the whole thing is just algebraic geometric notion. So in that case, this is always exact complex whenever Q is equal to or greater than P. So once they have this exactness of Skoda complex, then there was this work of Lazarsfeld and Lee saying that the multiply ideals actually have some special local algebraic property which is not shared by arbitrary integrally closed ideal. So the special property is that when you look at minimal first syzygy of this ideal J, which is actually the germ of the usual multiple ideal in the local ring, then it's not vanishing modulo m to the power n prime, which means that when you have these G1 through GB, and they're giving this syzygy, which is the relation between the generators Fi and the order of Gi at point x is less than n prime minus 1 for some I. So such n prime exists. That's the corollary coming from in this paper of Lazarsfeld and Lee. So when you want to extend the previous question of Lazarsfeld to the general PSH function cases, all you need to do is you need to prove the exactness of Skoda complex for the general singular weight. So this is okay. So this is explaining how this corollary is leading to the answer for Lazarsfeld's question. On the other hand, you can actually Lee constructed a particular integrally closed ideal which is not satisfying this property. So that implies that this particular integrally closed ideal cannot be a multiple ideal. So I'm sorry. So we already passed the statement of exactness of Skoda complex. So let me just go back to this statement. So when you allow general PSH function, you can still prove the exactness of Skoda complex for these range of Q's. It's not just Q bigger than P, but Q bigger than some larger value of P, larger function of P. So we prove this, but the method is very different from the case of algebraic PSH function. So I don't go into the proof, but I want to mention that the previous algebraic case of exactness of Skoda complex, what you use actually boils down to a vanishing theorem. So we already mentioned the natal vanishing theorem. So there's a version of this natal vanishing theorem, and then applying it, you get exactness of Skoda complex. So at first you could expect the same vanishing theorem could work for the more general case of exactness of Skoda complex, because for general PSH you still have natal vanishing. But it turns out things are not that simple, because the same method of using vanishing theorem cannot be used because there is this obstacle of the openness conjecture. So at first we didn't know there was this obstacle, and we naively thought the same argument will work with some simple tricks. But actually that was not the case. So instead of vanishing theorem, what you need to use is something called a very powerful tool from several complex variables. It's called Hermander's L2 estimate for D bar. So this is something originating from the classical analytic methods of Kodaira, when Kodaira first proved his vanishing theorem in the 1950s. What Kodaira used was something called Bochner-Kodaira method. So after Kodaira proved his vanishing theorem, basically algebraic geometers didn't want to use those analytic methods for algebraic geometry, but they found other algebraic methods to prove the same vanishing theorem. But on the other hand, not in algebraic geometry, but in several complex variables, those analytic methods were developed in another direction, and there was this tool of L2 estimator for D bar, which is basically solving D bar equation. So I'm sorry I don't have time what d-bar equation is, but maybe I should mention that our interest has been constructing some holomorphic objects, particularly holomorphic functions or holomorphic sections. And the definition of holomorphic is basically when you have a section of a line bundle and when you have this notion of d-bar operator, and when d-bar of f is 0, then f is holomorphic by definition. So solving this d-bar equation is closely related to constructing holomorphic objects. So actually, these methods, we used it for this particular problem of exactness of Skoda complexes. But actually, this is being used for many other problems in algebraic geometry. And maybe I should just summarize the comparison between these two terms in the title. So when we said algebraic methods, basically it means cohomology vanishing, such as Kodaira or Nadal vanishing, with respect to algebraic PSH singular weights. On the other hand, in many instances, you can replace the use of vanishing by this L2 estimate for d-bar. And so at first glance, this is quite interesting because vanishing is about shift cohomology, but L2 estimate for d-bar is not only about cohomology, but it's more about solving d-bar equation. So they are different, but you can think of L2 estimate for d-bar as some generalization of cohomology vanishing, because, for example, you can use L2 estimate for d-bar to prove many vanishing theorems. Okay, so what I meant in the title by analytic methods was this d-bar equation method and general PSH singular weights instead of algebraic PSH singular weights. So the importance of these analytic methods in algebraic geometry was recently first shown by this famous result by Yeomtong Siu. He had this famous result, invariance of plurigenera for arbitrary varieties. So I didn't write it down here, but it basically says when you consider we defined this canonical line bundle and also we defined its mth tensor power, and if you consider all the holomorphic sections in this line bundle and the vector space dimension, this is considered to be a fundamental invariant of this variety X. And here, invariance of plurigenera means this invariant, which is called plurigenera or plurigenus. This is invariant under deformation of X as far as when X deforms smoothly. So when you have a smooth family of X's and then you consider this plurigenus number, it is constant in the smooth family. So this nice result was shown by Siu in the arbitrary case. So you don't put any assumption on X. There's no restriction on the dimension and there's no restriction. So in such full generality, there's only the proof by analytic methods and there's no proof by algebraic methods. So I guess this is the most important example showing the difference between these two methods. Thank you very much.